So let's talk about the remainder of the MCQs that were most commonly missed. Let's see. I'll start with, now this is a secure exam, so I can't talk about the specifics of the problem, so I'm just going to kind of focus on the conceptual ideas and the things that it seemed like students messed up on. So if you have a planet with a satellite orbiting, most people don't realize it. Like, if this was the Earth, the actual low Earth orbit, where most satellites are, is much closer to the surface of the Earth. It's like skimming the surface if you were to look at it from outside. Really close. But usually, and they do this to throw you off, they do this to make sure you're paying attention, they'll tell you the orbital altitude. Right? The altitude. And let's just say that's 100 kilometers. And then they want to talk about the forces that are acting on, or let's say you want to calculate the acceleration of the satellite that's moving in a circular orbit, which means we would be looking for a centripetal acceleration, right? And then we would just use Newton's second law, which says that the net force is mass times acceleration. Really, there's only one force acting on the satellite, and it's gravity, and it's going to be a centripetal force. So we know it's going to be moving in a circle, well, at least if we're told that. So the net centripetal force, by the way, let me point this out, never label, not many people did it, but a couple did, never label a free body diagram with a force that you label centripetal. Okay, don't do that. Any force can be a centripetal force. Any force can be a centripetal force. So you label your free body diagram with the force. Is it a normal force? Is it a friction force? Is it a gravitational force? You label with those forces, and then you just know it's a centripetal force whenever you start applying Newton's second law. Okay? All done? All right, thanks, man. Have a good one. Okay. So the net force here is going to be the gravitational force. And that's going to be mass times centripetal acceleration, mass of the satellite. Mass of the satellite times the centripetal acceleration. But we know that the force of gravity is big G times the mass of the planet times the mass of the satellite over the distance between their centers of mass squared. And this is what always happens. Notice the mass of the satellite. Everyone brought mass of the satellite to the party. So our centripetal acceleration is gmp over r squared. And you could also say v squared over r. The point that I'm trying to make, though, is that a lot of people, for r, given this particular problem, will put in the altitude. And that is incorrect. You will always get a very, very wrong answer when you do that. What you must do is add the radius to the altitude to get the total distance between the centers of the objects. Okay? So you could have done everything right. Your brain could have been totally on board with what's going on, but you just used the wrong number, and so you get the wrong answer. Okay? So try to avoid that. Any questions? Okay. And since we're on this problem, this is covered in the other video, but since the picture's up here, let's just say hypothetically, not that this happened on this particular mock exam or not, but does the planet create a torque on the satellite? Who said that? Good job. There's no torque. Why is that?
It's directly, is it perpendicular to the
parallel, yeah. The position vector r is essentially 180 degrees to the gravitational force. And we know that torque is force times lever arm times the sine of the angle between them. In this case, the angle is 180, and the sine of 180 is 0. So 0 torque. which is why the satellite doesn't increase its angular velocity. Right? If it's in a perfectly circular orbit, then it moves in a circle at constant speed, constant angular speed. Right? Even if it's not in a circle, even if it's in an elliptical orbit, even if it was not even gravitationally bound and it's just moving through space, the force of gravity is always going to be 180 degrees to the position vector, or the R vector, the lever arm. Okay. Cool beans? All right. So let's say I take a spring and a vertical spring and I put a mass on it. And this is where it's at equilibrium. And then I push it down and press that spring a lot. And then I let go of it. Where's it going to be moving the fastest? At equilibrium, above, below? When is it going to be moving with the highest speed? At equilibrium. Good. This is simple harmonic motion. At the equilibrium position, the net force is 0, right? That's where the spring is going to be. That's where the spring force is now not exerted, kind of, but it's going to be balanced by the weight force. But at equilibrium, the net force on the object is going to be 0. The acceleration is going to be 0. The velocity is going to be max. And the kinetic energy is also at a maximum. Whether it's a pendulum or, in this case, a mass spring oscillator. At the amplitudes, the net force is a max. The acceleration is maximum. And that's what throws students off, because at the amplitudes, the velocity is 0. But it's also when you have the largest force and the largest acceleration. That's the point at which it's changing direction. It's being pulled. This guy would be either being pulled or pushed the hardest by the spring. And because it comes to a stop, the kinetic energy is 0. The potential energy is a maximum. In this case, at the equilibrium point, the potential energy is 0. So it's a little counterintuitive, but if you just think about the motion a little bit, you should be able to piece all. You don't have to remember all that stuff. You just need to understand. You need to understand the mechanics behind it. Okay. Okay, I'm just gonna talk about this concept briefly. I think that I didn't really cover it as well as I should have in class, but this year's been such a blur, I'm not really entirely sure. But center of mass velocity. For a system of objects is constant if no net external force. So if I have two objects that collide, two carts that collide and bounce off, the center of mass of that system is going to move at a constant speed the entire time. Say if this cart's moving this way much faster than this one, right? The center of mass will be between the two objects, but it'll be moving this way, since this guy's moving that way faster. And then after the collision, even if they bounce off, that center of mass velocity continues to travel at the same speed. I don't think I went over that. I feel like I didn't go over that well enough in class. I do apologize for that. So just remember this. Even if you have multiple objects that are all moving, if they're in a closed system, even if they're colliding with each other, even if they're moving in all different directions, the center of mass velocity of that system will be constant. Okay. I'm assuming all of you will take AP Physics C next year, especially you, Kurt. And so when you're in AP Physics...
I'm failing Physics A, so I can take Physics C next year.
Good plan. We'll talk about center of mass stuff quite a bit next year in Physics C. And again, I feel like I didn't really cover it too much. There's good stuff in the notes, the notes on April 20th module. Yeah, that's in the momentum section, I believe. Okay, so keep that in mind. What if we want to let's say we have hypothetically a problem where you have a turntable or a disk with a radius of 0.5 meters, rotational inertia 1 kilogram times meters squared, and it's initially rotating at 2 radians per second, and there's friction on the axle which is exerting a torque and causing it to slow down, and let's say it takes 10 seconds for it to slow down to a final velocity of 0. Find the average torque exerted on the disk due to the friction on the axle. Okay. Well, that average torque, to figure out that torque, I need, notice I'm given the rotational inertia, I'm looking for torque. If I had one other thing, I could figure out the torque. Remember, torque is the rotational equivalent of Newton's of force. Rotational inertia is the rotational equivalent of mass. Newton's second law relates force, mass, and acceleration. So if I know the mass and the acceleration, I can calculate the force. For torque, I need to know what? Rotational inertia and angular acceleration. And I mentioned this quite a bit when we were doing Newton's laws, maybe not so much when we were doing rotation, maybe I should have. But the acceleration is the thing that binds together Newton's laws and kinematics, right? Because acceleration is what's in the kinematic equations, and it's what's in Newton's second law. And so that's the thing, that's the key. Because I don't know what that is. I'm not told what that is, but I do notice that I have 3 kinematic variables, which means I should be able to find the fourth, angular acceleration. And that's just kinematic equation number 1 for rotation. It might be number 2 as listed on the formula sheet. But I can figure out the acceleration using final velocity equals initial velocity plus the acceleration times the time. Final velocity is 0. Subtract omega naught. Divide both sides by t, and I get the angular acceleration is negative omega naught over t. And it is negative. If we assume that we have a positive angular velocity to start with, then we must have a negative angular acceleration in order to bring it to a stop. All right? And then we just plug that in here. Torque is going to be rotational inertia times negative omega naught over t. If we got a negative angular acceleration, I got to have a negative torque. However, if the problem says what's the magnitude of the torque or some such, yeah, the average torque, sorry, can't read it. It probably asked you what the magnitude of the torque was, in which case you just drop the negative. Right? And so that would be 1 times 2 divided by 10 would be 0.2. Newton meters. Remember, torque is force times a distance, so it's a Newton times a meter. Newton meters, which is why you car people know foot-pounds, right? Pound is a unit of force, not weight, just like Newton.
Foot-pound is just the imperial?
Yeah.
Foot-pounds are just the imperial version of Newton.
Mm-hmm. Yeah, pound, remember, pound's force.
Yeah.
Pound is force, kilogram is mass. It's not the same. It's not the same.
They use grams in the metric system too. What do we use? What's our max?
It's like the slug or something.
Oh,
Something weird.
that's a thing.
Something that no one ever uses. Yeah.
Okay. That's odd.
I think it's the slug.
That's a weird word. Is it used in anything?
Hmm?
Is it used in anything?
I don't know. Maybe like some obscure, weird.
Not weird. I didn't
No. Because it's useless, pretty much. Okay. Let's say Kurt's driving his car
Really, really fast, like 120 miles an hour.
really fast, 120 miles an hour.
That's not really fast.
I know. But like in a 30, that's
You know what happens if you get in a wreck at 120 miles an hour? You die. And it's like,
well, it depends on who you get in a wreck with. If you get in a wreck with someone who's going 100 miles an hour in the same direction, it's just a 20 mile an hour crash.
that's true. Well, no, because you're going 100, you're still going 100 miles an hour relative to the ground.
If you just bump, but if you
Yeah.
spin out, then you're.
Yeah, then you're screwed. 100. Have you ever been 120 miles an hour?
That's really
That's
fast.
fast, dude. You're
Have you been
crazy.
100 miles an hour? Oh, okay.
How fast have you gone?
135.
Well, mine's like 50
Did your
miles,
car
it's
feel
not
like it
even
was
that
gonna shake
fast.
apart?
Right.
No, I just got new tires when I did it.
Okay. Hopefully you had a straight
Yeah,
road.
it was on track.
Okay. Good. Okay. And let's say that you stopped, you slammed on the brakes and skidded to a stop. If you skid to that means you're burning rubber, right? That means you're squealing. The tires have stopped rotating and then the car just slides to a stop. What type of friction is bringing you to a stop?
It is.
Oh,
Kinetic friction, right? Because the two surfaces are sliding in relation to each other. So the kinetic friction force is what's going to bring you to a stop. So you're going to have a speed V naught, and you're going to come to a stop right about here. A distance delta x away from the starting point. You call it distance d. Sometimes the problems will give you distance d, whatever. And this is the question. I can't read it because this is a secure exam, but the question essentially says, what do you need to know? What would you have to measure in order to find how much work friction did on the car? Okay, and this is something that accident investigators actually do. Obviously, they're not doing the physics out in the field. They use books that are written by engineers and physicists, but this is what they do. I mean, they make measurements of skid marks to try to figure out who's at fault, right? Especially if there's a lot of damage done, if people have been hurt very badly or worse. They need to know who's at fault. Very often the people are butting heads and arguing with each other. And just another reason to just drive safe out there. If you're going to drive 135 miles an hour, make sure you're on a controlled track, right? But what do you need to measure? And so those types of questions, my brain thinks mathematically. What do you have to measure? What measurements must you make? Measurements to determine the work done by friction. Which essentially is saying the change in kinetic energy, right? But if you're there after the fact, you can't measure the initial velocity, right? Because you weren't there. You weren't there when the skidding started.
Can't measure the time either.
Can't measure the time either.
You can measure the length.
You can measure the distance of the skid marks, yes. So that's one for sure, right? So let's talk about the math, though. If we're talking about the work done by friction, and if it said energy loss due to friction, energy dissipated in other forms, it means the same thing, right? We need to find the work done by friction. That's going to be the friction force times the displacement times the cosine of the angle between them. That's on the formula sheet. What's the angle between the velocity, the displacement d, and the friction force? Friction force is this way. Kinetic friction force.
180, right?
180, sorry. And then the cosine of 180 is?
Shoot, is it 1 or 0 or something? Or, no, that's wrong.
Negative 1. Remember, on the back of your formula sheet, it has the trigonometric values for all the common angles. 0, 30, 45, 60, 90, 180. Okay. So the work done by friction, as we would expect, is the negative friction force times the distance. Well, I know the friction force is proportional to the normal force. And the normal force is equal to mg. Right? The kinetic friction force is the easy one. It's just the coefficient of kinetic friction times the normal force. And I know the normal force based on my free body diagram is equal to mg.
So you'd have to know the mass.
Yeah, you'd have to know the mass.
And then wouldn't you have to know the frictional constant?
Yeah, the coefficient of kinetic friction, u
You
mg.
can't really measure
Yeah,
that.
yeah.
You have to.
No, you can.
But you can't like find it out before the experiment. It's really difficult, right? Like,
No,
you have to test it and then.
Yeah, but it's already known. It's already known. Most tires are made out of the same type of rubber. If they're specialty tires, then they just run the calculation again. If you're on asphalt, which most of the time you're driving on asphalt, they already know what this is.
Yeah.
So if you know that and you know the distance, and you can just look at the little tag on the inside cover of your doors when you open your doors, there's that little card there that tells you the mass of the car, or at least the weight. I don't know. But the only ones that made sense in this, like, you know, if you want to find the work done by friction, these are the things you'd have to know. That's why my brain usually goes to the equations for questions like that, where it says, what do you have to measure? What quantities would you have to measure in order to determine something like this? Well, then I try to find an equation that relates the quantities in question. And then just look at that equation and say, all right, well, what's in the list of choices that I can choose from that's in my equation there? On that note, I kind of let it fall on the wayside, but there are going to be some questions on the AP exam where you have to choose two answers. So be sure that you're ready for those. If I remember correctly, they're going to be the last ones, the last 5.
And pilot questions, or are they?
What?
Does the AP exam have pilot questions? Or does it?
Yeah, but not. I think so, but not that sure. Just know that if it says select 2 answers, you must select 2 answers, and you got to get them both right. If you get one right and the other one wrong, then you don't get it. Yeah, you get the whole thing wrong. So keep that in mind. It should be. I apologize if this is not the case, but I'm pretty sure it's the last 5. I'll verify that before tomorrow. Okay. I'm going to stop it.